So we will continue our discussion on single variable search methods. We saw the most primitive and most unimaginative one first, namely the exhaustive search, and we briefly touched upon this dichotomous search, right? I don't think I have given you the algorithm, and we have not worked out any problem on this. The dichotomous search, needless to say, it comes from the word dichotomy. What is the meaning of the word dichotomy in English? Okay, and it's also used in sentences like, I hope you are able to appreciate dichotomy between the two, means when you are able to appreciate the difference between two or whatever. So it means that you are dividing something into two equal parts, more or less two equal parts. The dichotomous search, we will try to we try to get those 2 points of evaluation very close to the center of the interval, so that every time you do 2 evaluations, you can get 50% of the interval, or you do 1 evaluation, you will get 25% of the interval, but there is no 1 point test. So you will always have even number of evaluations. Okay, so the dichotomous search is like this. So x equal to a to x equal to b, this is I naught. 0 always represents the original interval of uncertainty. Now the center, okay. Now you choose 2 points very close to the center. So right, so if you consider this, the distance between a and x2 is now I naught, okay. So the distance between x1 and, I don't have space to indicate there, the distance between x1 and b is also I naught plus epsilon by 2, okay. So the algorithm is like this. Choose 2 points at epsilon by 2, needless to say epsilon should be very small. For example, epsilon should not be I naught by 4, for example, then there is no point in, okay. Choose 2 points. Choose 2 points, let us say x1, x2, evaluate now use eliminate, how do you indicate that a, you will understand, or should I say a to x1? You will understand, okay. Of course, that is the third case of eliminating both to the left of x1 to the right of x2, if f of x1 equal to f of x2 is very rare, Numerically it is very rare because epsilon will be 0.001 something, unless the function is so simple, it is symmetric and all that, it will never happen. Is a proposed or desired accuracy. That is the algorithm, right? Divide I naught into two parts. Around the center, choose 2 points x1, x2 at epsilon by 2 from the center. Epsilon should be very small. Evaluate f of x at x1 and x2. Use the 2-point rule to eliminate the region to the left of x1 or the region to the right of x2. Okay. Proceed in a similar way means, that means whatever interval is remaining, take the center of that interval, have an epsilon, have 2 points epsilon by 2 from the center of the new interval, but each time you will get different points, right? If this is eliminated, here 2 points, from here 2 points and 2 points, and the points will never get repeated. You will have to compulsorily evaluate x1 and x2 every time you employ this procedure till your final desired accuracy is obtained. Now it should be possible for us to evaluate the reduction ratio of this algorithm. Obviously it is very powerful because every two evaluations 50% of the interval is cut. Shall we start writing down? How do you establish the reduction ratio of this algorithm? So after two evaluations, what is the new interval? After two evaluations, what is the new interval of uncertainty instead of I naught?
I naught square by 4.
I naught by 4. If you have to be not I naught by 4. I naught plus I naught plus epsilon by 2. Correct? The remaining interval will be this. What you are removing each time is I naught minus epsilon by 2. Is it clear? So you have to be alert. So after two evaluations, what remains is, okay, if epsilon is small, it is just I naught by 2, but after some time we will remove the epsilon. Now we will keep the epsilon. Now what is the reduction ratio for two evaluations? Or one iteration, whichever way you want to say. I naught divided by 2 I naught divided by I naught plus, or
2 by 1.
Okay.
2 I naught by 1.
Is it correct? Now if epsilon is much smaller compared to I naught, okay, if this is 1 meter, I take it as 5 millimeter. Which one? I naught is 1 meter, epsilon is 5 millimeter or 2 millimeter, it is okay. Then RR will be equal to, RR is equal to 2 to the power of 1. Okay, is that clear? Now I want to retain this, so shall I erase this portion of the board? Is everybody through with this? if we go through r iterations, if we go through one step, it is 2 to the power of 1. If we go through r steps, the reduction ratio is 2 to the power of r, not gamma. What is the relationship between the number of iterations and the number of evaluations? If n is the number of evaluations and r is the step number of the iteration, then the relationship between n and r is okay. If n is the number of evaluations, n equal to so I should say r will be whether this how much this approximately equal will be replaced by the equality sign depends on how small an epsilon you choose, but epsilon is finite and hence non-zero, therefore you will get a reduction ratio which is always smaller than this. If you take a big epsilon, then the reduction ratio will fall down substantially. Okay, for example, if n equal to 8, n equal to 8 dichotomous, yeah, tell me the RR, huh? Exhaustive, mm, 16 exhaustive, how much was it? 3.5, 3.5, 16, 256, what is this, huh? Yeah, so if n is very small, you don't see much difference between the RR of exhaustive and dichotomous, but as n increases, as the number of functional evaluations increases, either because you want an increased accuracy, or the function is so complicated that it is not very easy for you to figure out the optimum, it can be seen that the reduction ratio of the dichotomous search is far superior compared to the simple exhaustive search. So there is a need for anybody who is sane to study optimization. If somebody says no, I will divide the interval into 100 equal parts and evaluate the function, as stupid as it gets. Okay, for very simple problems, if you don't know any, what is called the naive, it is called the naive procedure. It's okay if it's one off and you'll never do optimization for the rest of your life. Otherwise, it stands to reason that we study optimization techniques. Is that okay? So this is the power of the dichotomous search. Now we will revisit the cylindrical water storage problem. We will just do 8 evaluations and you can see the power of this method. Unless we work out an example, certain things will not register. Okay. So for example, different people may take different epsilons, then finally they will come and argue that they are not getting the reduction ratio which is claimed on the blackboard and all that. So I will have to tell them what is the value of epsilon you have to choose. Is this fine? Okay. If I want to solve an optimization problem with the desired accuracy, how will I work using the dichotomous search? Because in life nobody will say I will do 16 evaluations, I will do 32 evaluations, I will do 64 evaluations. That's not going to work. Finally I say I want this with an accuracy of 0.01, 0.001. So you will start with the last step, you will start with the reduction ratio first. So the reduction ratio is very, very important. Reduction ratio is I naught by the new interval of uncertainty or the final interval of uncertainty. The final interval of uncertainty is the desired level of accuracy that will be in the denominator. You know the original interval of uncertainty I naught, from that you will calculate the RR. RR, if it is some complicated number, you will put it in a form such that you find the nearest equivalent where some 2 to the power of n by 2 will be equal to RR. Okay, from there you will find the number of n's, and then anyway you will start with dividing by 2 and dividing. So you will not expect you won't expect a convergence unless you have reached a n which is very close to what this formula has told you, right. So you won't get terribly impatient. What is this I am keeping on evaluating, I am not getting the accuracy because it requires 2 to the power of n by 2 evaluation, it requires n evaluations, okay, or 2n evaluations, whichever way you look at it, fine. Now problem number 30. 33, okay. Consider the cylindrical okay. Consider the cylindrical solar water heater storage problem. A is 2 pi r squared plus 2 pi r h, that is the surface area which you want to minimize, subject to the volume condition, volumetric constraint. The volume has got to be 4 meter cube, and the original interval of uncertainty is 3 meters. So we start with 0.5 and end with 3.5 meters. Use dichotomous search. And 8 evaluations. That means 8 functional evaluations, okay. All of you may take an epsilon of 0.01 meter, you may take an epsilon of 0.01 meter. If somebody does not like it, you can take 0.001 also, it becomes messy if you want to work it with your calculator. If you want, you can take 0.0001, there is no problem. Do not take something higher than this, 0.1 is no good, it will bring down your reduction ratio, okay. So okay, so this we have this here. So A, right. X1 equal to good 1.99 meters, X2 is 2.01, okay, get A of R1 and A of R2 and decide based on the 2-point rule, right. This is the first step. Vikram, what is the point? Huh? Not able to get something or? Huh?
Just trying to remember from the next one.
What is A of R1? Hmm? Okay, I have not. A of R1 is 28.9. A of R2 29 point. A of R1 is less than A of R2. So what can you say? It's a minimization problem. Region to the right of R2 can be eliminated. Okay, so that is the logical conclusion you arrive at after you do the 2-point test. Okay, region, because we are still talking about a unimodal function. Now, what is I1? Value of I1, not 1.5, 1.51, correct. So, R2 is so this remains. Now you bisect this. .51, 1.255. It gets messy, huh? 1.243. So you make it 1.25. So that is the center, is it? No, what is the center? 1.255. 255. So you can make 1.25 and 1.26. You are reducing the epsilon, no? You can take x1 as 1.25 and x2 as 1.26. No, what is it, Vinay? 2.1, 1.25 or 245? 245.
1.25.
The center is 1.25. X1 is 1.24.
Center is 1.255. So x1 can be 1.25, x2 can be 1.26. Don't get into the third decimal place, and or if you want, you can. I have no objection. You proceed. You will have three decimal places, 4 decimal places. It gets messier. I am just suggesting one way out, but you are free to.
Isn't the first iteration is used 0.003 because we are using epsilon by 2, but we
have to add epsilon by 2, sir. We added epsilon.
X1 will be 1.995.
Which one?
X1 is 1.995.
Find x1
Come again. What did I say?
So basically the interval is epsilon, sir, but we use 2 epsilon.
Yeah, then we change that to. What correction should we make to ensure that whatever you have done is correct? Epsilon equal to? Okay, take it. I don't want to rework. Okay. Take epsilon is equal to 0.02. Yeah. Okay, let's not repeat these. Now, don't call it x1 and x2, you will get confused. Already there is x1, x2. Proceed to x3, x4, x5, x6, right? x3 equal to 1.25 meter. x4 is 1.26, is that okay? I will write it a little bigger. If there are any objections, you can raise now. The center is between these two. You are sure? Samarjit is saying, vehemently he is saying no.
Center is 1.255.
That's okay.
Epsilon you've taken
You
0.02
take
now.
1.24 and 1.26.
Huh?
1.24 and
255. No, I change epsilon now. Dynamically I am changing. Why do we get saddled with the same epsilon? See, when it is 1.255, it seems to tell us that we better take 1.25 and 1.26, right? Something close to that, right? So the okay, we create rules so that it helps us to solve the problem, right? Now a of R3, a of it's not x3. I think we have to be clinically correct. This is R1, this is R2. This is R3, we are, the variable is radius. Okay. Okay, what is A of R3? 16.2. A of R4? 16 point. So A of region to the right of, okay, therefore region can be eliminated. Now third step. How many evaluations are over?
4.
Yeah, we need 4 more, right? We have to do it patiently. Yeah, tell me what is I2 now? I2. That is the interval at the end of 2 iterations or 4 evaluations. How it can become? Point? What is this? 0.76, okay. It should come down, right, with the iteration, otherwise we are not going the right direction. So shall we retell A is there, no? So R4 is what? 1.26. Now you take the center, R5, R6. What is the center now? 1.88. So what do you want to do? 0.789. So it is a dynamically changing epsilon. That's okay. Okay. So what we want to do is now R5 0.87 meter. That's okay. So long as epsilon is small, it's fine. We will ensure that this is not violated. We can take something smaller than this, but we do not want to take something which is larger than this. A of R5. A of R6. 9.6. Please remember that this is the answer, we are close to that. Right? 866 is the answer, but we are bypassing that, but that's the, we are not working out using a calculus based method, we are still searching, okay. That is why if you take 2 points R5 and R6, it is, the function is not changing so much, that itself gives an indication that you are nearing the optimum. Of course our interval, it takes a long time to come out to the dichotomous search, but it gives us some ideas about the nature of the function. So what do we say? Again AR5 is less than AR6, right? Always region to the right is eliminated, is it? That is very bad. Okay. So region I expect you to write all this in the, don't just put R1, R2, R3, R4 in the exam. You table or whatever, I want you to go through. Don't say, some people I have seen previous years, R1, R2, R3, R4, R6, it will be just like a, it will be like a table, and I won't know whether they really understood, whether they applied the algorithm properly, or it will just take a few more minutes to write it like this. Please be patient and write this out. Okay, now we just have 2 more iterations and then we are home. So we are now at the end of 6 functional evaluations. A equal to 0.5 and R 6. So what is I3 now? Point? How much? See by how much the interval has reduced by using 6 functional evaluations. Using 6 functional evaluations, 3 meters has come down to 39 centimeters. If you use exhaustive search in 6 iterations, how much would you have got? Half a meter, 0.6. As you keep proceeding, the difference will grow. Now, what about this? This is center. The last two R, R7, R8. What is R7? Please tell me. 0.69. R8. Okay. AR7 is greater than AR8. That is my intuition. Please do it. AR7 is greater than AR8. Therefore, region to the left of 7 can be eliminated. Is that correct? We are not going to do one more iteration, but we will leave it like this. Now A equal to, A is gone. R7 is 0.69, R6 I4 0.2. What is the RR? What is the RR? 15. What is expected? 16. Why is it not 16? Epsilon is not 0. Epsilon we change the point not 1. But if you take more pains and make epsilon very small, point not 1, you will get something like 15.5 or in the limit epsilon tending to 0, the RR will approach 2 to the power of n by 2. Okay, this is a pretty powerful method. So even if you had to solve a multivariable problem, some people what they do, why so much of fuss, repeatedly I am saying why so much of fuss about about having a sophisticated optimization technique for a single variable problem is, most optimization problems are multivariable problems. Each of these multivariable problems can be broken down to single variable problems. So what you can do is, you can keep all variables but one at some values fixed in a particular level of iteration, and then you optimize with respect to one variable using the most powerful single variable search algorithm. then change the variable and when you use a particular variable choose the best optimization technique available to you. Then after you are finished with one round of iterations for all the variables, then you go to the next round. That is one way of doing it. Okay, that is why in literature lot of papers are written on coming out with a very efficient single variable search algorithm. So the RR I naught where n is the number of functional evaluations. Okay, fine. Can you increase the reduction ratio beyond this? Is it possible to increase the reduction ratio beyond this? Intuitively the answer is no, because the best you could do is you could cut the interval by 50%. Anything less than that is suboptimal, correct? So if at all there is a technique which claims that it can have a reduction ratio which is superior to the dichotomous search, then what should support that claim? What is the logic which is possible?
Okay.
I want to use a 2-point test. Computational economy suggests that we have to use, don't say I will use 3-point test each time, and I want to use only, each of my functional evaluation comes with a cost of computer time. I may have to run these things on a supercomputer. So if somebody claims that he has come up with an algorithm which is better than the dichotomous search, does it sound like violating the Kelvin-Planck statement of the second law of thermodynamics? Huh? It is impossible to construct a device which when operating in a cycle will have its sole effect the production of work by having interaction with only a single reservoir. The Cauchy statement, let's not get into ME1 now. There are algorithms which are superior to this. So what is that funda? Please wait, I'll go through the history. So one of the most powerful single variable searches is basically the Fibonacci search. So it's quite obvious, it's quite apparent that it should be based on the Fibonacci sequence, right? The Fibonacci sequence should be employed. So Fibonacci, of course the name suggests that he was a Italian mathematician. Okay, I just maybe so he is supposed to be a celebrated Italian mathematician in the Middle Ages. Okay, so what is this Fibonacci series? Yeah, can you tell me the Fibonacci series? 1, 0 is there? Leave the 0. Okay, so this is basically the Fibonacci series. Any particular number in that series is sum of the two previous numbers. okay, for n greater than equal to is all right. Okay. Okay, how does Fibonacci enter the story here? Okay, so yeah, this fellow was there from 1170 to 1250 has developed all this, but optimization is relatively new, right? In 1953, a scientist called Kiefer, a mathematician called Kiefer, proposed in the journal American Mathematical Society proposed use of the series. What is the funda about this now? Any clues? Now I told you. The funda behind the Fibonacci search method is this. With a level playing field, nobody can beat the dichotomous search. So we have to do something shady. Okay. Okay, on a level playing field, you cannot beat the dichotomous. That fellow says 50%. I mean, how can we get better than 50%? All these fellows are saying I don't need 50%, but I will still argue you. The funda is the Fibonacci series is so beautifully suitable for this, because the sum of a particular the entry at a particular point, the number in the Fibonacci series in the sequence is equal to the sum of the previous two numbers. So if you are using a 2-point test, when you are always doing it in pairs, if you so choose the two numbers that one of the two numbers is already there which is evaluated, then each time you do the functional evaluation of a pair 2 points at a time, 1 point is already there. So it does not matter whether you have 50% or not, you have only 30%, does not matter, 35%, because one of the you do not do two evaluations at a time, it is only one evaluation at a time, because the other is already there. Very quickly, very rapidly it converges. Is it okay? So simple demonstrations like this, we look at the algorithm in the next class. For example, I naught equal to 8 meter, millimeter, kilometer, whatever you want, some appropriate units, x equal to 0, x equal to 8. I want to employ the Fibonacci series. Okay. So where is this 8? 8 is there, no? That is why I chose this. 8 is there here. Okay. The first 2 points are chosen in such a way. The first 2 points are chosen in such a way, they are at a distance of I naught into Fn minus 1 divided by Fn. So what is this? 8 into 5 by 8. Distance from either end. That means it is 5 from, it can't be so close now, that is dichotomous, right? So this is 5 units from this, so here it is 3 and here it is 5. So x1 is 5, the first point is 5, x2 equal to 3. Do not worry about whether how x2 can be smaller than x1, it does not matter, choose the 2 points. Certain portion of the interval will get removed. How much of the interval will remain? 5. Is that okay? See, either f of x, if you are looking at a minimization problem, f of x2 is less than f of x1 or f of x2 is greater than f of x1. In either case you will remove either 0 to 3 or 5 to 8. okay, you will have the interval which is remaining is 5. This is the first step. Next step, suppose I say the function is such that 0 to 3 is removed, okay. So what is remaining is x2 is equal to 3, this is x equal to 8, okay. Now what is remaining is 5. Up to this there is nothing great in the algorithm, nothing great, something you took some ratio, some arbit ratio and then got the 2 points, you did the functional evaluation. It is far inferior compared to the dichotomous search till this point because the funda is not yet in place. Now we will apply the funda. Now this one distance is I1 is equal to, this is equal to I1 into f of n minus 2 by f of n minus 1. What is this? 5 into, what is n minus 2? 8, 5, what is the previous number? 3 divided by 5. So what is the distance now? 3. So if you take the distance 3, you will have what this is x4 or x3? Huh? So this is only 3, so this will be x4. Okay, x4 is 5. The other one is x3 is equal to, oh, so this will be, oh, x3 equal to 6, x4 equal to 5. Agreed? But 5 was already evaluated. Why is this fellow behaving like this? Because f of n minus 1 plus f of n minus 2 equal to f of n. So you will start dividing like this, first iteration 55 by 89, then 34 by 55, 21 by 34, 13 by 21, 5 by 8, then you will come to half. That means you will just have one point in the center of the interval. But each time you divide, it so happens that one of the 2 points is already evaluated. Now with 3 points you will get a substantial reduction in the interval. How much will the interval reduce now? So finally you will be left with, you will be left with 3. In 3 evaluations you reduced, from 8 to 3 you reduced, okay. So we will formally state this in the next class. I will call this as A, B, f of n minus 1, f of n minus 2. We will prove this and then I will also tell you the algorithm. Then we will revisit the cylindrical water storage heater problem and using the Fibonacci search method we will see how this works, alright. But what is cumbersome about this method is there was some elegance in the dichotomous search, that any interval half, 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 but here it is somewhat ugly, right. Each time the ratio is different, the ratio with which you divide the interval, but people try to fix that also. We will see that in the next class.